Hello, Math 263 students. Right now, we don't have anyone on Zoom, but I'm going to go ahead and record our lesson for today so that those of you who are watching it later will have the opportunity to see what we need to take a look at in 7.2 and then also get into 7.3. So right now, we're going to take a look at 7.2. 7.2 is titled Substitution. And substitution is going to be a technique to help us with integration, or we could also say to help us with anti-differentiation. So to get our feet wet and to help our brains work this morning, let's go ahead and just try a couple antiderivatives. So let's just do two. Let's say we have x squared minus 2x plus 5. We're integrating all of that with respect to x. So just some terminology recap, we call the part I've underlined in purple our integrand. Our variable that we're looking at is x, indicated by our dx part. This part is not optional, we have to have it on there. It tells us that we have to have the independent variable match up with what we see there. So if we remember from 7.1, the rules we want to use here are mainly power rule, and also splitting things up into 3 pieces. So if I think about integrating just the x squared component, I know I'm going to have an x cubed term, but I have to divide by that new power, so x cubed. And then if I think about integrating 2x, well, I don't have to worry about the minus. I can go ahead and pull that out. And if I wanted to, I could think about just the x squared part first. And I could say, well, if I had x squared, the derivative would be 2x. So I really just need minus x squared. Or you could also go through the idea of pulling that negative 2 out in front, dividing by the 2 when you bump up your power, and then canceling those. Either way works. In other words, you could also do this. So pull out that negative 2. And then you could say, since you have x to the first, then your new exponent is going to be 2 divided by 2. But then notice those 2's cancel and give you back what you started with. Then from the 5 term, the antiderivative of 5 is 5x. The antiderivative of a constant is always that constant times the variable. And then since an antiderivative is just one solution, and the general solution or the antiderivative that they're asking for here is really a family, we need to add in that plus c. So in this case, our full solution is x cubed minus x squared plus 5x plus c. So let's do one other example. Actually, let's do 2 to contrast them. 2 that were similar to what we did last time. Let's do 2 e to the x and e to the 2x. So for the first one, I would probably think about taking this 2, and even if I don't take the step of writing it on the outside and writing again, visually I'm separating it and really just focusing on the e to the x side, because I can pull that constant out. And when I think about the antiderivative of e to the x, the antiderivative of e to the x is itself, because the derivative of e to the x is itself. So what we really want to have is 2 times e to the x, and then we can just tack our plus c on at the end. So if we differentiated 2 e to the x, you get back 2 e to the x, which is your integrand. So let's take a look at how this changes with e to the 2x. We actually looked at some of these. Were very similar to last time, and it kind of takes us into the idea of 7.2. We were actually thinking through the ideas of substitution together without calling it that. So we're really just going to be diving a little deeper into the technique we used when we handled this. So we might have said, well, it's not going to be e to the x, because if I differentiate e to the x, I get e to the x, right? I don't get that 2. And it's not going to be 2 e to the x with the 2 in front, like the number 2, because that's still going to give me my constant in front and not the 2 as the coefficient of x in the exponent. Then we might say, okay, well, I could try something like, I'm going to put a question mark as a guess here, e to the 2x. And if we were to try e to the 2x, we know that if you differentiate e to the 2x, you get e to the 2x times 2, or 2e to the 2x. So that's not quite it, because we're going to have an extra multiple of 2. But to combat that, what we did last time is we said we could divide by 1/2, manipulate those constants. And we wrote down the rule for the antiderivative e to the kx. So in this case, that first guess wasn't right, but 1/2 e to the 2x is going to give us back e to the 2x when we differentiate. So the antiderivative of e to the 2x with respect to x is 1/2 e to the 2x plus c. Now, this idea, you could approach a different way and organize your thoughts with what's called a u substitution. So I want to show you how that works, and then we'll expand it to different ideas, different problems. So let's focus on that e to the 2x for a minute. You want to think about that 2x as an inner function. We could even think about calling it a u, just like we did when we were trying to differentiate e to the 2x. We thought about that as an inner function, and then we said differentiate e to the power, and then do the derivative of the power. So we were finding derivatives. So we're working backwards here. So it's like we have to undo this, essentially. So if we think about u, my purple here, u equals 2x, then I want you to think about u prime. Instead of calling it u prime, let's call it du dx. So u dx is going to be 2. And then what we're going to do is multiply by that dx, separate out those differentials, and this is going to be du equals 2 dx. So notice that we can't just swap this dx for a du. What we would like to be able to do is rewrite this with that u as our independent variable. But we don't want to mix a u and a dx. We want, if we're using x's, to use dx. If we're using u's, to have du. But I can't just swap them because they don't equal each other exactly. I could either write, if I had 2dx, replace it with du, or another solution is to say, well, if I'm looking to replace my dx, that's going to be 1/2 du. Place it right there. Then what happens is that's a constant. And I can now just pull that constant out. So when we compare, we're not done with the problem because we haven't found the complete antiderivative yet. But we've made this problem look like the antiderivative of e to the x with respect to x by doing it as e to the u with respect to u. So if I think about u's, this is just 1/2 e to the u plus c. And then think about your original problem. That u was really a 2x. So we can back substitute, put that 2x back in. And notice that's the same thing we got, 1/2 e to the 2x plus c over here, where we had to kind of do more of a guess and check. So this is called a formal u substitution, or a u sub. And I like to think about a u sub as helpful in the fact that it helps me organize my thoughts. But oftentimes, once you get comfortable with it, sometimes we can skip writing down the u sub. I don't recommend that yet. And we're not going to do a ton of these u subs. We're going to try to scratch the surface and do a few. So try to get familiar with and try to get comfortable with writing this u, and then only if you feel really comfortable with it, kind of skip it and go on. In a lot of problems though, as they get progressive and more difficult, especially if you end up taking math classes later, which may not be the case for most of you, but a few, you'll learn how to use u substitutions in more and more complicated problems. So let's take a look at another one. Let's say we have the integral of 2x e to the x squared, all with respect to x. So the integral, or the antiderivative, This is called an indefinite integral. Let me write that down. So sometimes I'll just say the integral, but it's an indefinite integral, which is the same thing as an antiderivative. Sometimes the notation and just the vocabulary is tricky as we keep changing it, keep adding to it. We're going to see some connections on why it's called an indefinite interval coming up. We're going to contrast it with a definite in 7.3. So when I take a look at this one, first of all, it's a little bit different than the other one in that instead of e to the 2x, it's e to the x squared. Then the other big difference is that there's a product, and we're doing the reversal of a product, but we haven't really done any products per se. And it turns out that when you have products in your enneagram, it can be difficult to do those without another rule, unless you're doing a U substitution. So if you can look at this problem and realize, hey, if I think about my x squared as an inner function, the derivative of that inner function almost matches up with what I see. Then you're going to be set up to do a U sub. So let's go down the details of that. So we've got u equals x squared, du equals dx, or sorry, du dx equals 2x. So du equals 2x dx. In other words, if I want to change these variables out, my du and dx are not equivalent, and there's more to it than just a constant multiplication. So when I transform this, I want you to focus on the pieces that match up. I'm going to box in the 2x dx. All of that is going to be replaced with the du, and e to the x squared is the u. So if I do this u substitution and swap out the u and the du for the x and the dx's that I see, then the antiderivative is just e to the u plus c. Then when I back substitute, I'm going to have to put that x squared back in. And if you wanted to check it, we would have to differentiate e to the x squared and think about utilizing chain rule, and we should get back our integrand for the original part of it. So let's try another one that's kind of like this. I'm going to vary this one just a little bit. So let's say we have 10x squared e to the x cubed. Now, you can kind of see that I'm playing around with similar problems to what we've been doing, but with a twist. We have a new inner function on that exponent. And what has to happen in this case for us to be able to do a successful U substitution is the leftover components have to be pretty close to our du. So if I think about what my du dx is going to be in this case, then what I would really need to match up is 3x squared dx. But I don't quite have a 3x squared dx. Now I could, if I wanted to, go ahead and try to divide by 3 and multiply by 10 to get the 10. I'm going to show you a slightly different technique. The 10 doesn't match with the 3, so I'm going to go ahead and pull the 10 out. In other words, isolate it. And then I'm going to think about how to get that 3 in there. Life would be perfect if we just had a 3, right? But we can't just multiply by a 3 because that is not balanced. If we multiply by a 3 inside our integrand or our integrand, we also have to balance it so we're not changing the equation. Keep in mind, the 10 was there originally, but when I put in the 3, I have to balance it with the 1/3 so that I'm not changing my expression. So now let's just clean this up a little bit. What I have right now, I'm going to ignore that 10/3 on the outside. And then the reason I did all of this is so that this piece becomes my e to the u, and all of the rest of this is going to become my du. So let's go ahead and try to squeeze it in here. This becomes 10 thirds e to the u du. So I'm going to break that. We know that's going to be 10 thirds e to the u plus c. And then we just have to backside. So, is it quick? Not necessarily. Sometimes it requires a little bit of guess and check still. What is our inner function? Do I have what I need? And how do I need to manipulate it? But what it allows us to do is expand what we can handle. Now, I've been giving us examples with exponential functions, but we can also see some places this comes in handy for power functions and variations of power functions. So let's take a look at another example. So for this one, let's say we have the antiderivative of x times the quantity x squared plus 1 to the 10th power. Now, one option, not a good option, but one option for us is to expand this into a polynomial. So think about maybe if this 10 were 2. X squared plus 1 squared means we could do x squared plus 1 times x squared plus 1, multiply it out, distribute our x, and get an expanded polynomial. It wouldn't be quick, it wouldn't be easy, but then we could break it into pieces. However, if we wanted to save ourselves some work, we could notice that this looks like an inner function. We could think about our inner function as x squared plus 1. All of that gets raised to the 10th. And then if we think about the derivative of that inner function, the derivative of that inner function would really be 2x, which almost matches up. It's just off by a constant, off by multiplying by a constant in this case. So what we see here is that if we had the 2, this is kind of another way, instead of solving for the x dx, we could also put the 2 in here and multiply by the 1/2 on the outside to get the 2 we want and keep it balanced. So then this becomes u to the 10th. So here's our component u to the 10th. And then we're going to replace the 2x dx with our du. So this becomes 1/2. Power rule on this guy. Add 1, divide by that new power, so u to the 11th over 11. Let's see. So sometimes these guys get a little bit messy. And keep in mind, we still have to back sub. If your original problem had an x, you want to go ahead and back sub so that you have an x in the final answer. I just want to look back and make sure we got everything in there. Looks good. So let's take a look at just another variation there. Actually, let me change this just a little bit. I'm going to change it to make it doable reasonably 2 ways. So in this particular case, there's 2 ways to do it. The original method of multiply and expand that out, 2x plus 1 times 2x plus 1, do FOIL, and then split up your pieces, integrate that polynomial. That works. But if you can notice, it's kind of like the previous problem, and we could try a u substitution, things will work out quickly. So if I think about a u sub here, like I have an inner function, but notice there's nothing being multiplied out in front. But when we think about this u, the derivative of our linear u is going to be a constant. Du dx is 2 in this case. So du is 2 dx. So all we really need is a 2. I'm going to put the 2 in front just because that's my habit. You could also put it right in front here if you're multiple. And then if you were adding in that multiplication by a constant, we also need to divide by 1 over that constant. So when all you're missing is the constant piece, you can take care of that. What you can't take care of is an x. You can't just multiply by x, divide by x on the outside. That doesn't work, unfortunately. So let's go ahead and note that our 2x dx, that's all going to become a du. And this part is going to become a u squared. So let's finish it up. Ignore your 1/2. The antiderivative of u squared is u cubed over 3. Let's see. So we're going to have 1/2 times 1/3. What's that? 1/6. And then let's go ahead and substitute our u. So 2x plus 1 to the 3rd. So we covered 2 major types, exponentials and then essentially power functions that have inner functions. You can also occasionally have some ones that can be trickier. So I'm going to show you an example of another u sub that I think is just a different way of thinking about your u sub. Once you get the hang of it, it's not any harder, but maybe something like this. The antiderivative of 2x divided by 1 plus x squared dx. Now, part of the reason this makes harder is partially because of what we can't do. You can't just take the antiderivative at the top, divide by the antiderivative at the bottom. Just like we had a complicated quotient rule for derivatives, you can't just split up an antiderivative with quotients. You can do that with sums and differences, addition and subtraction. You can't do it with division and multiplication. Because if we could split it up, we know how to take the antiderivative, just the top and just the bottom. But altogether, we're stuck. But what we want to do is think about how the top and the bottom are related. And this requires a little bit more being clever. Now, if I am trying to set the stage for this one, the rule that we're going to have to use in the end is going to be this one. And at the moment, it doesn't seem related, but we're going to see how it ties in. We know that the derivative of the natural log of x, in fact, would be the natural log, the absolute value of x, is going to be 1 over x. And last time we said that the antiderivative of 1 over x is the natural log of the absolute value. Just like you really needed to memorize the rule for natural log, you really need to memorize the antiderivative of 1 over x, because it's one that we often forget about. It just feels different, right? It doesn't seem as intuitive, and we don't practice it as much as the power rule and the exponentials sometimes. So let's take a look at how this relates. This relates because this guy is really a quotient. And what I'm seeing in this, when I look at it, is I'm seeing something on bottom and then a derivative that matches up. So here's a technique. When you have a quotient and it doesn't seem like you can do anything with it, split it up so that you're isolating 1 over the bottom and you pull that top out as a multiple. Because if you remember, if you cover up that dx for a second, if you multiply 2 fractions, over 1, you multiply the tops, multiply the bottoms. So then you can just undo the fraction by 1 over the denominator times the numerator. So no problem with writing this. But now, when I do this, it allows me to see that this 1 over something is similar in form to this, right? It's not 1 over x. It's 1 over 1 plus x squared. But what I want you to think about is all of this piece as being your inner function. Once you see it, it'll make a little more sense. But if we let that inner function be 1 plus x squared, our du dx is going to be 2x. So our du is 2x dx. So in this case, this stuff really becomes my du, and this becomes 1 over u. So we've actually simplified this to 1 over u du. Now, we know that this should be the natural log of the absolute value. We didn't have to do any constant manipulation. And then I can go ahead and put this back in. Replace my u with 1 plus x squared. Now, in this particular case, you don't technically need the absolute values. It's fine to leave them, but 1 plus x squared is never negative because that x squared can never be negative. So when you add 1 to it, you're always positive. Don't stress about it. I would accept either of those two last lines. Always better to leave the absolute value if you're not sure if you can remove them than to take them off. Now, the reason I think this one is trickier is a less obvious u substitution. When you look at this original part, you're not seeing a composition. So let's take a look at another example that kind of feels similar. One over 2x plus 3. Now, this one may be a little bit easier for our brains to think of because it looks a little bit more like that 1 over x. It's a variation of 1 over x. So we don't really have a numerator that we need to worry about putting out, but we do have this idea of an inner function. It's just that is all on the bottom. So in this case, du dx is 2, so du equals 2 dx. And notice what we don't have if we start transforming this. Our fraction is going to turn into 1 over u, but I don't have the 2 to replace 2 dx with du. So what I could do is multiply it in. You can multiply to the front or at the back like this. I always do the front to just have it. But this becomes 1/2, and then all of this part is going to be my du. Then this gives me 1/2 natural log absolute value of u plus c. And in this situation, I've got to leave that 2x plus 3 alone inside that absolute value because 2x plus 3 can be negative if you have negative x values, or some negative x values at least. All right, guys, so practice these u substitutions. It's going to be a very short homework set for 7.2. We're going to focus on quantity and, no, I said that wrong, quality and not quantity. So we're going to kind of stick with these 3 types. Ones where you have exponentials, power functions, and then u substitutions with a natural log. All right, guys, so that's it for this part. I'm going to stop this one and then start a new one because we're going to talk about 7.3 with the PowerPoint. Back in my video here.